Imagine standing in the middle of a silent, endless desert at night completely alone. You close your eyes and a faint breeze brushes past you, carrying whispers of something ancient, something invisible. You can't see it, you can't hear it, but it's there passing right through you, untouched and unfelt. This isn't just wind, it's the universe itself, speaking in the language of ghostly particles called neutrinos. Every second, trillions of them stream through your body like you're made of nothing at all. They've been doing this since the dawn of time, silent witnesses to the birth of galaxies, the collapse of stars, and the very fabric of reality. And yet, we've only just begun to unravel their secrets. What if I told you there's an entire cosmic fossil hiding in plain sight, a relic from the Big Bang itself, older than light, older than atoms? It's called the Cosmic Neutrino Background, and it's one of the most elusive and mysterious phenomena in existence. These neutrinos are the universe's oldest surviving messengers, carrying echoes of a time when everything was compressed into a space smaller than a single atom. They've traveled across 14 billion years to reach us unchanged, unbroken, and brimming with riddles we're only starting to decode. Today, we're diving into 25 of the most mind-bending puzzles hidden within this invisible ocean of particles. Why do they barely interact with matter? How do they shape the cosmos we see today? Could they hold the key to dark matter or even the fate of the universe itself? This isn't just a story about science, it's a detective story, a cosmic treasure hunt where every clue leads to more questions. By the end, you'll never look at the night sky the same way again, because now you'll know it's not empty. It's alive with ghosts. Picture the universe in its first second, a seething, unimaginably dense soup of raw energy. At that moment, for every single atom that would later form galaxies, stars, and planets, the cosmos created a billion neutrinos. They flooded existence like an unstoppable tide, and here's the strangest part: they never left. Today, 66 billion neutrinos pass through every square centimeter of your body every second, night and day, whether you're awake or asleep. But you'll never feel them. No alarm sounds when they arrive. No shadow is cast when they leave. They are the universe's most abundant particle and its most ghostly. Scientists call this the Cosmic Neutrino Background, and it's the oldest intact signal from the Big Bang, older than the cosmic microwave background, older than the first starlight. While photons from the early universe were trapped in a fog of plasma for hundreds of thousands of years, neutrinos streamed freely, untouched, carrying snapshots of the cosmos before planets or stars even existed. So why can't we see them? Neutrinos barely interact with matter at all. Most will fly through a light year of solid lead without a single collision. Catching one is like trying to trap smoke with your bare hands. That's why detectors like supercomputer and had to get creative. This Nobel Prize-winning experiment buried itself deep underground in a Japanese mine, filling a massive tank with 50,000 tons of ultra-pure water. Even then, only a handful of neutrinos per day would graze an atomic nucleus and release a faint blue flash, barely enough to confirm their existence. The puzzle isn't just detecting them, it's figuring out why the universe made so many. Did they sculpt the cosmic web of galaxies? Are they hiding secret branches of physics? One thing's certain: these invisible particles hold stories we've only begun to read. The cosmic neutrino background should be freezing cold, colder than the void between galaxies, colder than the cosmic microwave background's faint glow at 2.73 Kelvin. But when scientists calculated its temperature, the numbers didn't add up. The neutrinos whispered back a baffling reply: 1.95 Kelvin. Just slightly warmer than it should be. At first glance, the difference seems tiny, less than a single degree. But in the quantum realm, even a fraction of a degree is a screaming anomaly. It's like finding a snowball that refuses to melt in the heart of a volcano. So what's heating these ghostly particles? The answer might rewrite physics. When the universe was a fiery newborn, neutrinos decoupled from matter earlier than photons, those carriers of light that make up the cosmic microwave background. They should have cooled faster, left colder by the expansion of space. Instead, they're oddly warm. One theory points to dark matter. What if these invisible cosmic specters are tangling with something even more mysterious? Dark matter particles might have transferred energy to neutrinos long after their decoupling, like shadowy hands reheating a fading ember. Or perhaps the answer lies beyond our 3 dimensions. In theories like string theory, extra dimensions could have funneled energy into the neutrino sea from hidden realms of reality. Imagine a cup of coffee sitting in a room. Suddenly, heat seeps into it from an invisible 4th spatial dimension. The coffee warms without any obvious source. If extra dimensions exist, they might be the unseen stovetop keeping the cosmic neutrino background just a little too cozy. Then there's the chaos of the early universe itself. The first second was a battleground of forces we barely understand: inflation, phase transitions, particles flickering in and out of existence. Maybe neutrinos got caught in the crossfire, absorbing energy from quantum upheavals lost to time. Every fraction of a degree in their temperature could be a scar from a violent event we've yet to discover. This isn't just a numbers game. That tiny discrepancy holds the key to something monumental. If dark matter tweaked the neutrino background, its fingerprints are hiding in that temperature gap. If extra dimensions are real, their signature might be written in those fractions of a Kelvin. The universe's oldest ghosts aren't just relics, they're detectives carrying clues to physics beyond Einstein, beyond the Standard Model, beyond everything we think we know. The mystery isn't why they're warmer, it's what they're trying to tell us. Neutrinos are the ultimate cosmic chameleons, shapeshifters that transform as they race across the universe at nearly the speed of light. Imagine tossing a coin into the air and watching it spin heads, tails, heads again. Only this coin can morph into 3 entirely different versions of itself mid-flight. That's the bizarre reality of neutrino oscillations. These particles exist in 3 distinct flavors: electron neutrinos, muon neutrinos, and tau neutrinos. But unlike, say, an apple staying an apple, a neutrino born as one flavor can spontaneously switch identities over vast distances, flickering between all 3 states like a quantum kaleidoscope. Now picture this phenomenon unfolding not just in a lab or a supernova's fury, but across the entire observable universe within the cosmic neutrino background itself. Here's the catch: these oscillations aren't just random flickers. They're governed by the particles' masses, and that's where things get cosmic. Neutrinos shouldn't have mass according to the original Standard Model of physics, but they clearly do, because oscillations require mass differences between flavors. The problem: we still don't know which neutrino is the heaviest or lightest, a puzzle called the mass hierarchy. Think of it like trying to weigh 3 invisible feathers in a hurricane. The CNUB's neutrinos are so sparse and elusive that tracking their oscillations is like listening for a whisper in a crowded stadium. Yet this whisper could rewrite reality. If electron neutrinos turn out to be the lightest, it would confirm the normal hierarchy, a ladder of masses matching other particles we know. But if they're the heaviest, that inverted hierarchy would flip our understanding of quantum physics on its head, hinting at entirely new forces or symmetries nature has been hiding. And then there's the cosmic scale. Over billions of years, even tiny mass differences would warp how these neutrinos clump, slingshot around galaxies, or subtly tug at the universe's expansion. Some theories suggest their oscillations might have left faint fingerprints in the cosmic web, those sprawling filaments of galaxies we see today. It's as if the universe's largest structures were sculpted, in part, by the quantum whims of its smallest particles. The wildest twist: neutrinos might not even be playing by the rules we wrote for them. Certain models propose sterile neutrinos, ghosts beyond the 3 flavors. that could be oscillating undetected, weaving through the sinew bee like invisible threads. If true, these phantoms could be dark matter itself or portals to hidden dimensions. Every oscillation we catch is a breadcrumb leading deeper into the quantum wilderness. So why does this matter? Because the sinew bee isn't just a fossil, it's a live broadcast from the universe's first second, and neutrino oscillations are its static. Decode that signal, and we might finally hear what the cosmos has been trying to tell us. There's a ghost haunting our models of the universe, one so elusive, even its existence is in question. Scientists call them sterile neutrinos, and if they're real, they could be the heavyweight champions of the neutrino world. Unlike the three known flavors, electron, muon, and tau, these phantom particles refuse to interact with any force except gravity. No electromagnetic handshake, no nuclear embrace. They're cosmic hermits passing through walls of lead like they're not even there. The plot thickens with experiments like mini Buoni at Fermilab. Designed to study neutrino oscillations, it began picking up strange excess signals, more electron neutrinos appearing out of thin air than the standard model could explain. It's as if someone kept adding extra puzzle pieces that don't fit the picture on the box. One tantalizing possibility: these anomalies are whispers of sterile neutrinos, briefly flickering into existence before vanishing like quantum mirages. Their mass could dwarf ordinary neutrinos, think a bowling ball hiding among feathers, yet their invisibility makes them nearly impossible to corner. Where does the cosmic neutrino background fit in? If sterile neutrinos exist, they'd be swimming in this ancient sea, their gravity subtly warping how ordinary neutrinos dance across the cosmos. Picture a crowded ballroom where most dancers are light on their feet, but a few invisible partners move with slow, deliberate steps, tugging the rhythm of the entire room. The sinew bee might hold the key to spotting these heavyweights by their gravitational shadow. The stakes couldn't be higher. Sterile neutrinos could be dark matter itself, those missing puzzle pieces that make up 27% of the universe. Or they might hint at extra dimensions, their mass a fingerprint of hidden folds in space-time. Every experiment hunting them is like trying to catch smoke with a net made of moonlight. Yet if we succeed, it could tear open the standard model and rewrite the rules of reality. The universe's oldest particles aren't just relics, they're hiding a secret family, and we're just starting to trace their outlines in the dark. Dark matter is the universe's most frustrating jigsaw piece. We see its gravitational footprints everywhere, from spinning galaxies to the cosmic web's grand architecture, yet it refuses to show its face. But what if we've been overlooking the one place it's been hiding in plain sight? Somewhere in that ghostly sea of the cosmic neutrino background, there could be a bridge between the ordinary and the invisible. Take neutrino portal theories, for example. Imagine a locked door between two rooms, one filled with light, the other pitch black. Neutrinos might be the key. In these models, certain high-energy neutrinos from the sinew bee could decay into dark matter particles, like cosmic alchemy transforming whispers into shadows. It's not magic, it's quantum tunneling on a universal scale. These portals wouldn't just connect particles, they'd tie together two of cosmology's greatest mysteries. The implications are staggering. If even a fraction of the sinew bee's neutrinos decayed this way, they could have seeded the universe with dark matter during its infancy. Picture a cosmic conveyor belt, ancient neutrinos born in the Big Bang's fury, slowly decaying into the invisible scaffolding that now holds galaxies together. The math gets eerie. Certain decay rates would neatly explain why dark matter outnumbers visible matter 5 to 1. It's as if the universe handed us a recipe written in neutrinos, and we're only now deciphering the ingredients. But how do you hunt for something that decays invisibly? Enter the next generation of telescopes. Instruments like the European Space Agency's Euclid or NASA's upcoming Nancy Grace Roman Space Telescope won't just map galaxies, they'll scan for subtle distortions in starlight caused by dark matter's gravity. Hidden in those distortions could be the fingerprints of CNUB decays. Galaxy clusters, those massive cities of stars, might be especially telling. Their immense gravity acts like a magnifying glass, amplifying any faint signals from decaying neutrinos. There's another twist: temperature. If dark matter particles were born from CNUB decays, they'd carry a specific energy signature slightly colder than ordinary neutrinos, like ice melting into water. Future detectors like Ptolemy, designed to catch relic neutrinos directly, might spot this thermal mismatch. It'd be the smoking gun, proving that dark matter wasn't just hanging around, it was forged from the universe's oldest particles. Of course, skepticism lingers. Some models suggest sterile neutrinos as a dark matter candidate, while others propose entirely new particles. But the beauty of the CNUB is its versatility. It's a cosmic laboratory frozen in time. Every neutrino is a time capsule from an era when dark matter might have taken its first breath. Whether through decays, collisions, or some quantum sleight of hand, these ghostly particles could finally lift the veil on the universe's darkest secret. And here's the kicker: if we're right, the key to solving the dark matter puzzle wasn't in some distant galaxy or high-energy collider. It's been here all along, streaming through your hands as you read this, silent, unseen, and waiting to be understood. Every particle in the universe carries a kind of fingerprint, a unique set of properties that defines how it interacts with the world. Electrons have charge, protons have mass, and magnets. They have a dipole moment, that invisible north-south pull that makes compass needles swing toward Earth's poles. But what if I told you neutrinos, those ghostly passers-by, might be hiding their own magnetic secrets? The idea sounds impossible at first. Neutrinos are famously aloof, barely reacting to anything, no electric charge, almost no mass. Yet some theories suggest they could possess a vanishingly small magnetic dipole moment, a quantum quirk that would let them interact with magnetic fields like microscopic compass needles. If true, it would shatter expectations, rewriting the rules of particle physics overnight. Here's where the cosmic neutrino background becomes a time machine. These ancient neutrinos have been cruising through space for billions of years, threading through galaxies, galaxy clusters, and the sprawling tendrils of the cosmic web, all while swimming in primordial magnetic fields far older than stars. If neutrinos do have a dipole moment, their journey would have left faint twists in their paths, like a hiker veering slightly off course because of a hidden magnet in their backpack. The challenge: detecting this effect is like listening for a single wrong note in a symphony playing at the edge of the universe, but new experiments are rising to the task. Projects like Ptolemy aim to trap relic neutrinos in ultra-cold graphene, watching for the tiniest wobble as they pass through controlled magnetic fields. Even a whisper of deflection would be revolutionary proof that neutrinos, against all odds, carry this ghostly magnetism. The implications spiral outward. A neutrino dipole moment could explain why the universe favors matter over antimatter, solving one of cosmology's biggest puzzles. It might also hint at undiscovered particles, heavy, right-handed neutrinos predicted by theories beyond the standard model. These shadowy siblings could have imprinted their magnetism onto the CNUB like a cosmic stamp, leaving clues in the oldest particles we can trace, but the real drama lies in those primordial magnetic fields. Billions of years ago, they were far stronger, woven into the fabric of space itself during the universe's violent birth. If neutrinos interacted with them, even faintly, their collective motion could have sculpted the large-scale structure of the cosmos, tilting galaxy clusters, warping filaments of dark matter, leaving patterns we're only now learning to read. So why hasn't anyone found this dipole moment yet? The signal would be impossibly faint, buried under quantum noise and cosmic interference. It's like trying to spot a single firefly's glow from across a city. But with next-generation detectors and AI-driven analysis, we might finally catch neutrinos in their magnetic act. And if we do, the universe's oldest ghosts will have handed us a new law of physics written in the silent language of spin. The universe has a glaring asymmetry, one so fundamental it shapes everything from atoms to galaxies. For every particle of matter, there should be an equal opposite, antimatter. Yet look around, the stars, planets, and even your own body are made of matter. Antimatter is vanishingly rare, as if the cosmos picked a favorite in some grand cosmic coin toss. This isn't just curiosity, it's one of physics' greatest unsolved mysteries. If matter and antimatter had been perfectly balanced, they would have annihilated each other in the Big Bang's aftermath, leaving nothing but light. Instead, for every billion antimatter particles, 1,000,000,001 matter particles survived. That razor-thin margin is why anything exists at all. Now, rewind to the universe's first microseconds. A sea of particles and antiparticles boiled in the extreme heat, colliding and annihilating in flashes of energy. Among them were neutrinos and antineutrinos, but here's the twist. They might not have been perfect mirrors. According to leptogenesis, a theory that ties neutrinos to the matter-antimatter imbalance, these ghostly particles could have decayed ever so slightly differently from their antimatter counterparts. Imagine two identical clocks, one ticks a fraction faster. Over time, that tiny difference adds up. In the early universe, neutrino decays might have produced a slight excess of electrons over positrons, nudging the scales toward matter. The cosmic neutrino background is the smoking gun. These relic neutrinos, frozen in time, could preserve traces of that ancient asymmetry. If their modern-day counterparts exhibit certain behaviors like violating CP symmetry, where particles and antiparticles don't behave identically, it will be strong evidence for leptogenesis. Experiments like T2K in Japan are already hunting for these discrepancies by firing neutrino beams through detectors, watching for telltale signs that neutrinos flip flavors differently than antineutrinos. But the real breakthrough could come from the CNUB itself. If we could measure relic neutrinos directly, a Herculean task, their energy spectrum might reveal a faint bias toward matter. Picture a deck of cards where one suit is subtly stacked. That imbalance, imprinted 14 billion years ago, could explain why the universe didn't vanish into pure radiation. Of course, alternatives exist. Some theories propose heavy right-handed neutrinos that decayed asymmetrically, while others point to primordial black holes or even quantum foam fluctuations. Yet leptogenesis elegantly ties two mysteries into one: the neutrino's odd properties and the universe's missing antimatter. It's a cosmic detective story where the culprit might be hiding in the oldest particles we can trace. The stakes couldn't be higher. If neutrinos tipped the balance, they didn't just shape the universe, they made it possible. Without that 1 in a billion advantage, there'd be no atoms, no stars, no us. Every galaxy is a monument to that asymmetry, written in the language of ghostly particles. And if we're right, the answer isn't in some distant nebula, it's streaming through you right now, whispering secrets from the dawn of time. The universe has a way of defying expectations, especially when it comes to its most elusive inhabitants. Take neutrinos streaming through the cosmic neutrino background. These particles are so light, they were long assumed to drift freely across the cosmos, barely noticing the gravitational pull of galaxies. But recent simulations reveal something startling. These ghosts might be gathering in invisible halos around massive galaxy clusters, like moths drawn to a flame they can't touch. How does something with 1/1,000,000th the mass of an electron get trapped by gravity? The math gets wild when you scale up to cosmic proportions. While a single neutrino barely responds to a galaxy's tug, trillions of them, each moving just a fraction slower than light, add up to a subtle collective drag. Picture a crowd of marathon runners hitting a patch of mud. Individually, they'd barely slow down, but en masse, the entire group shifts pace. Similarly, as neutrinos pass near galaxy clusters, their combined gravitational interactions could create neutrino halos, diffuse clouds clinging to these cosmic giants. Detecting these halos would be like spotting candlelight from across a continent. But physicists have a clever workaround: gravity's lensing effect. When light from distant galaxies bends around a massive object, it distorts like a funhouse mirror, betraying the presence of unseen mass. Normally, we attribute this to dark matter, but if neutrino halos exist, their combined gravity should leave an additional micro-lensing signature, a faint second layer of distortion buried in the data. Telescopes like the Vera Rubin Observatory are scanning the skies for exactly these whispers, passing starlight for hints of neutrino clumping. The implications could upend cosmology. If neutrinos cluster more than predicted, it might mean they're heavier than we thought, or that gravity behaves differently on cosmic scales. Some modified gravity theories, like MUND, already challenge Einstein's framework. A neutrino halo detection might tip the scales, forcing us to rewrite the rules of how mass warps spacetime. Then there's the dark matter connection. If sterile neutrinos, those hypothetical heavy cousins, exist, their halos could be masquerading as dark matter's fingerprints. The cosmic web's faint filaments might not be woven just from shadowy unknowns, but also from these barely their particles, their gravity amplified by sheer numbers. The paradox cuts deep. Neutrinos were supposed to be the universe's loners, indifferent to the clumping and clustering that define galaxies. Now we're finding they might be active participants in cosmic architecture, their subtle gatherings hiding in plain sight. It's a reminder, even ghosts leave shadows if you know where to look. The cosmic neutrino background should be smooth, a pristine fossil from the universe's infancy, its energy spread evenly like a perfectly tuned radio signal. But what if it isn't? Hidden in those ghostly particles could be faint ripples, tiny spikes and dips in their energy spectrum that betray violent events from the dawn of time. Imagine listening to a symphony and hearing, beneath the music, the echoes of long-forgotten explosions. That's the hunt for distortions in the CNUB, and the clues they carry could rewrite cosmic history. Take ancient supernova. In the universe's first few 100 million years, the earliest stars, monstrous behemoths hundreds of times heavier than our Sun, lived fast and died violently. Their catastrophic explosions would have flooded space with high-energy neutrinos, some of which might have tangled with the cooler, relic neutrinos of the CNUB. The result, subtle bumps in the energy spectrum, like waves crashing into a calm sea. Spotting those bumps would be like finding fossils within fossils, evidence of the first stellar deaths imprinted on the Big Bang's afterglow. Then there's the jet-setting drama of primordial black holes. If these hypothetical relics existed, their ferocious gravitational pull could have accelerated nearby neutrinos to blistering speeds, creating high-energy tails in the CNUB's distribution. It's as if a cosmic particle accelerator had been running in the background for billions of years, its handiwork hiding in plain sight. Even stranger, some theories suggest black hole jets might have injected neutrinos into the CNUB, like uninvited guests crashing a party and leaving their mark on the guest list. Detecting these distortions is like trying to read a book where every letter is written in vanishing ink, but projects like Ptolemy are rising to the challenge. This groundbreaking experiment plans to trap relic neutrinos using ultra-cold graphene sheets, monitoring for minuscule energy deposits, some as tiny as 1,000th of an electron volt. To put that in perspective, it's like measuring the weight of a snowflake by watching how it bends a beam of sunlight. If successful, Ptolemy could map the CNUB's spectrum with unprecedented precision, revealing those elusive ripples. The payoff, a cosmic timeline written in neutrino energy. A spike at a specific frequency could date the first supernova. A dip might signal an era of black hole activity. Together, they'd form a hidden narrative of the universe's wild youth, a story no telescope could ever see. These distortions aren't just noise, they're the universe's way of keeping secrets in the one medium that never fades, particles that outlasted time itself. Cosmic inflation rewrote the rules of reality in the universe's first trillionth of a second, a runaway expansion that stretched space itself faster than light, smoothing wrinkles and planting seeds for galaxies. But inflation didn't just shape matter and energy. It may have left its fingerprints on the cosmic neutrino background in ways we're only beginning to grasp. Picture this: as space-time ballooned, neutrinos already flooding the cosmos were stretched thin, their distribution imprinted with quantum ripples from that explosive moment. Those ripples aren't just relics, they could be hiding in plain sight, woven into gravity itself. Here's the breakthrough. Inflation didn't just stretch space, it generated gravitational waves, undulations in the fabric of reality that still echo today. Normally, these waves are faint whispers buried under cosmic noise, but neutrinos might amplify them. As the CNUB's particles streamed through the early universe, their sheer density could have subtly warped these gravitational waves like a stone distorting ripples on a pond. Next-gen observatories like LISA, a space-based gravitational wave detector, aim to catch these twisted signals. If they succeed, it wouldn't just confirm inflation, it could reveal which version of inflation we're dealing with. Some theories suggest inflation wasn't a one-time event but a fractal process, birthing countless bubble universes with different physics. If neutrino gravity interactions in the CNUB carry a specific signature, say, a preferred direction or pattern in the waves, it might hint that our universe collided with another bubble long ago. Think of it like finding seashells on a mountaintop, evidence of a flood that reshaped the landscape. The stakes are cosmic. If LISA or future probes detect these twisted gravitational waves, they'll do more than unlock inflation's secrets. They'll test whether our universe is alone or just one page in an endless multiverse story written in neutrino code. Quantum mechanics tells us that particles can be waves, that an electron isn't just a tiny dot but a blur of probability spread across space. But what if this wave nature doesn't just apply to subatomic scales? What if it stretches across galaxies? That's the dizzying possibility hiding within the cosmic neutrino background. These ancient particles might still be behaving as quantum waves over incomprehensible distances, their fates intertwined across millions of light years through a phenomenon called quantum coherence. Picture throwing two pebbles into a still pond. The ripples spread outward, intersecting and interfering in intricate patterns. Now replace the pebbles with neutrinos from the Big Bang and the pond with the entire observable universe. If these neutrinos have remained coherent, their wave functions unbroken, they'd be engaged in a cosmic dance of interference, their quantum states delicately linked no matter how far apart they've drifted. The mind-bending implication: the CNUB could be the largest quantum system in existence, a web of entanglement woven across 14 billion years. But here's the catch. Quantum coherence is fragile. A single interaction with matter, a brush with a magnetic field, even the subtle tug of gravity can collapse a wave function into a definite state, a process called decoherence. Most quantum experiments struggle to maintain coherence across a room, let alone a galaxy. Yet the CNUB's neutrinos have barely interacted with anything since their birth. They've been left alone, undisturbed, for epochs longer than stars have existed. If anything could preserve quantum weirdness on cosmological scales, it's them. This isn't just philosophical musing. If CNUB neutrinos are still coherent, they could be our best shot at testing quantum gravity, the holy grail of modern physics. Theories like loop quantum gravity or string theory predict subtle changes in how quantum systems behave under extreme spacetime curvature. Normally, we'd need a black hole's edge to see these effects. But coherent CNUB neutrinos have traversed the universe's entire gravitational landscape, from inflationary stretches to galaxy cluster collisions. Their wave functions, if we could read them, might carry scars from spacetime's quantum graininess. Even wilder, we might not need a telescope to find proof. Tabletop experiments like the Fermilab holometer are already hunting for quantum fluctuations in spacetime itself. If CNUB neutrinos imprint their coherence onto gravitational waves or dark matter distributions, these lab-scale detectors could catch echoes of that primordial quantum whisper. It's as if the universe left us a message in a bottle written in neutrino waves, waiting to be decoded by a machine the size of a desk. Of course, skepticism lingers. Decoherence from cosmic microwave photons or dark matter interactions could have scrambled the CNUB's quantum signature long ago. But if the signal is there, buried in the noise, it would rewrite our understanding of reality. Quantum mechanics and general relativity have been at war for a century. The cosmic neutrino background might finally broker peace, not in a collider or a Chinese letter, but in the quietest, oldest particles drifting through your hands right now. Neutrinos are cosmic survivors, particles that outlasted supernova, black holes, and the boiling chaos of the Big Bang itself. But what if even these ghostly titans have an expiration date? Hidden in the cosmic neutrino background could be a ticking clock counting down to their slow, invisible decay. The math seems unthinkable. If relic neutrinos are vanishing, transforming into even lighter particles across billions of years, it would rewrite our understanding of the universe's total mass, energy, and ultimate fate. The controversy starts with IceCube, a detector buried in Antarctic ice that's picked up baffling signals. While most high-energy neutrinos pass through Earth like it's not there, a fraction interact, producing faint flashes of light. But some of those flashes don't match expectations. They're dimmer, sparser, as if a percentage of neutrinos vanished en route. One explanation: they're decaying along the way like cosmic fireflies blinking out mid-flight. Here's the problem. According to the standard model, neutrinos should be stable. Without electric charge and barely any mass, there's no obvious pathway for them to break down. Yet if IceCube's data holds, we're staring at a paradox. Either our models are missing a quantum backdoor, some exotic interaction that lets neutrinos decay, or we've misjudged their masses entirely. This isn't just academic. The CNUB's neutrinos contribute to the universe's total mass budget. If they're decaying, even at a glacial pace, it would mean the cosmos is lighter than we thought. That tiny adjustment ripples outward. Galaxy clusters would spin differently, the cosmic web's structure would shift, and our estimates of dark energy's influence might need recalibration. It's like realizing the foundation of a skyscraper has been quietly eroding, millimeter by millimeter, for billions of years. Alternative explanations abound. Maybe IceCube's anomalies stem from neutrino interactions with dark matter, or an unseen fourth flavor oscillating into oblivion. But if decay is real, the implications are staggering. The CNUB isn't just a fossil, it's a candle burning down, its faint light carrying secrets about time itself. And if neutrinos can fade, what else in our universe might not be permanent? Black holes are the universe's ultimate cosmic shredders, devouring stars, bending light, and warping space-time beyond recognition. But what happens when something that barely interacts with anything meets something that consumes everything? That's the puzzle at the heart of the cosmic neutrino background's dance with supermassive black holes. These gravitational monsters lurking at the centers of galaxies might not just swallow neutrinos, they could twist, scatter, or even amplify them in ways that leave ghostly fingerprints across the cosmos. Take the Event Horizon Telescope's groundbreaking image of the black hole in M87. While its fiery accretion disk stole the show, something far subtler might have been hiding in the shadows. As CNUB neutrinos streamed toward the black hole, a fraction would have skimmed perilously close to its event horizon, the point of no return. General relativity predicts these particles wouldn't just vanish. Their paths would spiral violently, some flung outward like cosmic slingshots while others plunged into oblivion. The result, a faint but detectable shadow in the neutrino sky, a void where relic neutrinos should be but aren't. Neutrino telescopes like IceCube or the proposed Pacific Ocean neutrino experiment could one day map these absences. Imagine tracing the outline of a black hole not with light, but by the neutrinos it blocks, like finding a silhouette in a snowstorm by watching where flakes suddenly disappear. The kicker, since CNUB neutrinos come from all directions, stacking data over years might reveal a 3D neutrino shadow, exposing how black holes distort space on scales we've never probed. But the plot thickens. Some theories suggest black holes don't just absorb, they alter neutrinos passing nearby. In the extreme gravity well outside an event horizon, space-time curvature could redshift relic neutrinos' energy, stretching their wavelengths like taffy. Alternatively, quantum effects near the horizon might trigger rare neutrino oscillations, flipping flavors at rates impossible in empty space. It's as if black holes are cosmic laboratories, running forbidden particle physics experiments we can only glimpse from afar. Then there's the wild card, neutrino amplification. Just as black holes can focus light into bright Einstein rings, they might concentrate neutrino flows through gravitational lensing. Certain trajectories could funnel relic neutrinos into detectable spikes, bright spots in an otherwise uniform sea. If future instruments catch these anomalies near known black holes, it'd be smoking gun proof that the CNUB isn't just a backdrop. It's in constant, dynamic conversation with the universe's most violent objects. The implications ripple outward. If black holes leave neutrino shadows, their shapes could test general relativity's limits under extreme conditions, revealing whether Einstein's equations hold or crack near singularities. And if neutrinos oscillate differently near event horizons, it might hint at new physics beyond the standard model, where gravity and quantum mechanics finally shake hands. Every missing or warped neutrino is a breadcrumb leading deeper into the labyrinth of spacetime itself. So next time you see that iconic black hole image, remember, there's more to the story than meets the eye. Hidden in the darkness could be the whisper of ancient neutrinos, some silenced forever, others twisted into new forms, each carrying secrets from the edge of reality. The universe isn't just expanding, it's simmering with invisible turbulence, a chaotic dance of particles caught in the gravitational tides of cosmic nothingness. Picture the cosmic neutrino background not as a placid pool but as a storm-tossed sea, its waves shaped by the sprawling voids and filaments that weave through the cosmos like invisible highways. Supercomputer simulations now reveal these relic neutrinos don't drift smoothly. They swirl, eddy, and crash against the scaffolding of reality in patterns so vast they make hurricanes look like ripples in a bathtub. At the heart of this turbulence are cosmic voids, regions of space so empty they stretch hundreds of millions of light years across with barely a galaxy to break the monotony. You'd think nothing happens there, but neutrinos tell a different story. As these ghostly particles stream through voids, the lack of gravitational pull lets them race ahead like marathoners hitting open road. Meanwhile, in the dense filaments of the cosmic web, those threads of dark matter and galaxies connecting the universe, neutrinos lag behind, caught in traffic jams of spacetime curvature. The result, a cosmic weather system where high-pressure neutrino fronts collide with low-pressure troughs, creating currents that twist and knot across billions of years. Recent simulations from institutions like the Flatiron Institute bring this drama to life. Using algorithms that crunch decades of calculations in weeks, they've mapped how relic neutrinos behave like fluid dynamics on a galactic scale. One simulation showed neutrinos sloshing around a massive void like water circling a drain, their paths warped so dramatically that their energy distribution fingerprint could be detected by next-generation telescopes. Another revealed neutrino whirlpools near galaxy clusters, regions where particles spiral inward at near light speed, their collective motion subtly tugging at the fabric of spacetime itself. These patterns aren't just cosmic eye candy, they're fossilized turbulence from the universe's first second, when quantum fluctuations during inflation seeded all future structure. The neutrinos, remember, their swirling paths encode data about how gravity sculpted the cosmos, offering clues to mysteries like dark matter's distribution or the true geometry of the void. Imagine reconstructing a storm that raged 14 billion years ago by studying the ripple marks it left in a particle sea older than starlight. But the real shock came when simulations matched observational quirks. Astronomers have long noticed peculiar velocities galaxies moving slightly faster than dark matter models predict. Neutrino turbulence could explain it. Like wind-pushing sailboats, these relic particle currents might be giving galaxies an extra nudge, their cumulative effect tweaking the cosmic web's evolution in ways we're only starting to measure. The deeper implication: the universe isn't just shaped by gravity and dark energy, it's a battleground where invisible particle weather has been stirring the pot since the beginning. Every void isn't empty, it's a neutrino wind tunnel. Every filament isn't static, it's a neutrino superhighway with its own traffic laws. And if we learn to read this turbulent sea, we might finally understand why the cosmos looks the way it does, one ghostly current at a time. The cosmic microwave background gets all the glory, the afterglow of the Big Bang captured in stunning maps, revealing the universe at 380,000 years old. But what if I told you there's an even older photograph buried in the cosmos, one taken not in the universe's infancy, but in its first breath when time itself was barely a second old? That's the magic of the cosmic neutrino background. While the CMB shows us a baby universe after it had cooled and settled, the CNUB is a fossil from the nursery itself, frozen in the seething chaos of creation. Think of it this way: the CMB is like stumbling upon a faded, weathered manuscript from ancient times, still legible, but smudged by centuries of handling. The CNUB, on the other hand, is that same text written in indelible ink on unbreakable glass, preserved exactly as it was the moment the ink dried. Why? Because neutrinos, once they decoupled from matter just 1 second after the Big Bang, stopped interacting with anything. No plasma fog, no galactic collisions, no stellar explosions could alter their course or energy. They've been sailing through the cosmos untouched, carrying pristine data from an era before atoms, before protons, even before quarks had settled into their roles. This purity makes the CNUB a Rosetta Stone for pre-quark physics. The universe at 1 second old was a place beyond imagination, a broth of particles and energies so extreme, our particle colliders can't even approximate it. Quarks and gluons hadn't yet coalesced into the protons and neutrons we know. Gravity might have been just as strong as the other fundamental forces, a radical idea that could rewrite quantum theory. The CNUB's neutrinos passed through all of it, their properties subtly shaped by conditions we can only theorize about. Here's where it gets thrilling. The CMB's photons were born in a late universe, after quarks had already formed hadrons, after matter had mostly settled into familiar patterns. But the CNUB's neutrinos, they're eyewitnesses to the quark-gluon plasma phase, that exotic, soup-like state of matter where the rules were still being written. If we could read their energy spectrum with enough precision, we might spot anomalies, tiny deviations from what the standard model predicts, that betray the presence of unknown particles or forces active in that primordial inferno. Imagine finding a single typo in that unbreakable glass manuscript. A word spelled wrong, a phrase out of place. It wouldn't just be a mistake, it'd be evidence of a scribe we never knew existed. Similarly, a kink in the CNUB's neutrino energy distribution could hint at particles that vanished long before quarks dominated, relics of a more symmetrical universe where forces we now consider distinct were once unified. Some theories, like grand unification theories, predict such particles heavy, short-lived beasts that decayed instantly but left their mark on the neutrino sea. There's another layer to this time capsule. While the CMB was scrambled by the universe's expansion and the clumping of matter, the CNUB's neutrinos experienced none of that. Their distribution preserves the original density fluctuations of the cosmos, uncontaminated by later cosmic drama like galaxy formation or dark energy's influence. It's like comparing a photo of a calm lake at dawn to one taken after a storm. The CNUB shows us the undisturbed surface, revealing the true shape of the seabed beneath. Future experiments like Ptolemy aim to extract these secrets by capturing relic neutrinos directly. If successful, their data could answer one of cosmology's biggest questions: did inflation really happen? The CNUB's patterns, if aligned with inflation's predictions, would confirm that the universe underwent that exponential stretch in its first moments. But if they deviate, if the neutrino distribution shows unexpected irregularities, it might point to alternative theories like a bouncing universe or cyclical models. The irony is poetic. The universe's most aloof particles, the ones that refuse to interact, might be its most honest historians. While light and matter tangled and obscured their past, neutrinos kept their silence, and in that silence preserved the clearest echo of the beginning we're ever likely to hear. If you lined up all the neutrinos in the universe by weight, you'd expect a tidy order, lightest to heaviest, like stepping stones across a stream. But nature loves a curveball. The truth is, we don't even know if neutrino masses have a proper staircase, let alone which flavor stands where. This isn't just housekeeping, it's one of particle physics' most urgent mysteries, and the cosmic neutrino background might hold the key. Start with the flavors: electron, muon, and tau neutrinos, each paired with their charged counterparts in the standard model. But here's the twist: these flavors don't correspond neatly to distinct masses. Instead, neutrinos exist in quantum superpositions of mass states, oscillating between flavors as they travel. It's like having three differently weighted coins that keep morphing into each other mid-toss. The critical question: which flavor links to the heaviest mass state? Are electron neutrinos the featherweight's normal hierarchy, or the anchor's inverted hierarchy? Picture this cosmic weigh-in as a balancing act with the fate of physics hanging in the scale. In a normal hierarchy, the mass gaps between states resemble those of other particles, orderly, predictable. But flip it inverted, and suddenly the lightest known particles in existence would have a mass structure unlike anything else in nature, hinting at radically different physics governing their origin. The difference is subtle, a matter of fractions of an electron volt, but the implications could topple theories. Enter the CNUB. These relic neutrinos have been oscillating for 14 billion years, their flavor composition frozen in time like a snapshot of the early universe's preferences. Future detectors aiming to catch them directly, like Ptolemy, could analyze that flavor mix for clues. Here's why: oscillation probabilities depend on mass differences. Over cosmic distances, normal vs. inverted hierarchies would leave distinct statistical marks, slightly more electron neutrinos surviving in one scenario versus the other. The challenge: untangling this requires precision beyond anything we've achieved. Imagine trying to census a city's population by counting 3 people who vanish whenever you glance away. But breakthroughs in quantum sensors and ultra-cold trapping might soon make it possible. Some models suggest relic neutrinos could even carry phase information, quantum imprints of their journey, that would reveal their mass hierarchy outright, like finding a fossil with its DNA intact. And then there's cosmology's stake in the game. The mass hierarchy affects how neutrinos clump around galaxies, skewing large-scale structure in ways telescopes like Euclid could spot. An inverted hierarchy might leave neutrino halos with unique gravitational fingerprints, subtly warping space-time differently than their normal ordered cousins. The stakes: everything from neutrino-less double beta decay experiments to theories of why the universe has more matter than antimatter hinges on this ordering. It's not just about labeling particles, it's about whether the cosmos follows the playbook we know or one we've yet to imagine. Every relic neutrino streaming through you is a voting ballot in this quantum election, and we're finally learning how to tally them. Reality might not be as smooth as it seems. Beneath the fabric of spacetime, at scales a billion trillion times smaller than an atom, the universe could be a seething, frothing chaos known as quantum foam. Theorized by physicist John Wheeler, this is where gravity and quantum mechanics collide, a realm where tiny bubbles of spacetime constantly pop in and out of existence, warping the very geometry of the cosmos. And drifting through this turbulent sea, the cosmic neutrino background's ancient particles, possibly interacting with this foam in ways that bend the laws of physics as we know them. Think of quantum foam like an ocean's surface during a storm. From a distance, it looks calm, but up close, it's a frenzy of collapsing waves and swirling eddies. Now imagine a neutrino sailing through that chaos. Most of the time, it glides undisturbed, but at Planck scales where spacetime itself becomes grainy, even these ghostly particles might stumble, their paths jostled by the foam's fluctuations. The result, subtle aberrations in how neutrinos oscillate or decohere over billions of years, anomalies that could reveal quantum gravity's fingerprints. Here's where it gets stranger. Some models, like string theory's brain-world scenarios, suggest quantum foam isn't just froth. It's a membrane separating our universe from hidden extra dimensions. Neutrinos, with their barely their interactions, could be the only particles leaky enough to slip through. Picture a house with invisible rooms. Neutrinos might be the draft sneaking under the door, carrying traces of those unseen spaces back into our world. If relic neutrinos from the CNUB have spent eons tunneling in and out of these dimensions, their energy spectrum or oscillation patterns might bear scars of the journey, like finding sand from a secret beach in your hallway. Experimentalists are already hunting for these whispers. Projects like IceCube and future observatories could spot neutrino anomalies that defy the standard model, perhaps events where neutrinos momentarily disappear or arrive with unexpected energies. These wouldn't just be glitches, they'd be clues that relic neutrinos are brushing against quantum foam or even tunneling into other dimensions. It's like listening to a radio and hearing static from a station that shouldn't exist. The implications could redefine reality. If CNUB neutrinos encode Planck-scale physics, they'd be our only direct link to the universe's most elusive frontier, a place where space and time cease to behave. Every oscillation, every flavor shift might hide a deeper language, one where gravity and quantum mechanics finally speak the same tongue. The cosmic neutrino background isn't just a fossil, it's a cipher, and spacetime's foam holds the key. The universe's first moments were a frenzy of quantum chaos, a trillionth of a second when spacetime stretched faster than light, smoothing wrinkles in reality itself. We've long studied inflation's echoes in the cosmic microwave background, but what if the clearest signal isn't in light at all? Buried within the cosmic neutrino background could be a handful of ultra-rare particles that didn't just witness inflation. They were forged by it, carrying spin signatures no other neutrinos possess. These wouldn't just be relics, they'd be time capsules from the instant the universe went from quantum foam to cosmos. Here's why these inflation-born neutrinos would stand out. During that explosive stretch, particles weren't just pushed apart, they were quantum mechanically squeezed, their properties locked into configurations impossible under normal physics. For neutrinos, this could have imprinted a unique spin polarization, like a cosmic barcode distinguishing them from later arrivals. Most CNUB neutrinos decoupled a second after the Big Bang, but these inflationary outliers would have been flung free even earlier, escaping the primordial plasma with their spin signatures intact. Spotting them would be like finding a single grain of sand on a beach that glows in a color no other grain emits. The challenge, they're needles in a galactic haystack. For every inflationary neutrino, there are trillions of ordinary relic neutrinos drowning out their signal. But physicists have a plan. Neutrino telescopes tuned to hunt not just energy or direction, but quantum spin. Imagine a detector so precise it could filter neutrinos like a polarizing lens filters light, isolating only those with the telltale twist inflation left behind. Projects like the proposed IceCube Gen 2 or the Pacific Ocean Neutrino Experiment are inching toward this capability. using ultra-sensitive photodetectors to capture not just if a neutrino hits, but how it spins upon arrival. The real breakthrough would come from combining data across multiple detectors. Inflationary neutrinos wouldn't just have unique spins, they'd be distributed in a specific pattern across the sky, their density variations mirroring the quantum fluctuations that seeded galaxies. By mapping neutrino polarization alongside their arrival directions, astronomers could reconstruct a 3D snapshot of the universe's first trillionth of a second, a window far earlier than the CMB's 380,000 years. It'd be like comparing a toddler's baby photo to an ultrasound. One shows the infant, the other reveals the spark of life itself. There's a tantalizing symmetry here. Photons from the CMB gave us our first baby picture of the cosmos. Inflationary neutrinos could deliver the conception video, and if their spin signatures match predictions from theories like cosmic inflation or loop quantum gravity, we wouldn't just confirm how the universe began, we'd glimpse what came before. Every other particle we've studied emerged from the aftermath. These neutrinos might be the only things left from the firestorm that started it all. Dark energy is the universe's silent puppeteer, stretching space itself faster and faster, driving galaxies apart in an endless cosmic retreat. But what if this mysterious force isn't acting alone? Tucked inside the cosmic neutrino background could be an invisible accomplice, a pressure so subtle it's been overlooked for decades. Picture the CNUB not as a passive relic but as an active player. It's trillions upon trillions of ghostly particles exerting a collective push against gravity's grip. The math is dizzying. If each neutrino contributes even a whisper of repulsion, their combined effect across 14 billion light-years might be nudging the cosmos apart faster than dark energy ever could alone. This isn't just a tweak to the equations, it's a revolution in waiting. Most models treat the CNUB as a cosmic afterthought, its neutrinos too light and sparse to matter. But controversial theories like those from physicist Christian Beck suggest otherwise. Imagine blowing up a balloon covered in tiny weights. Normally, gravity would pull it downward, but what if the air inside wasn't just neutral but actively pushing outward? The CNUB's neutrino sea could be doing exactly that, its quantum mechanical pressure acting like an anti-gravity force on scales so vast it mimics dark energy's effects. The smoking gun, anomalies in supernova data. When astronomers measure the universe's expansion using distant stellar explosions, some observations don't quite match predictions. The discrepancies are tiny fractions of a percent, but they hint that dark energy's strength might vary over time or space. If the CNUB's neutrino pressure fluctuates due to its quantum wave nature, it could explain these wrinkles in the data. Regions where neutrinos are more densely packed would push back harder against gravity, subtly tweaking how fast space stretches there. Then there's the galactic weirdness. Spiral galaxies rotate faster than visible matter alone should allow, a phenomenon usually credited to dark matter's pull. But some simulations now show that CNUB neutrinos, if their pressure opposes gravity in just the right way, could mimic dark matter's effects without needing invisible particles. It's a radical idea that the universe's two greatest mysteries, dark energy and dark matter, might both trace back to the neutrino sea's ghostly influence. Critics argue the numbers don't add up, that neutrinos are too lightweight to muster such cosmic clout, but proponents counter with quantum field theory's quirks. In a vacuum, particles like neutrinos aren't truly at rest. They're fizzing with zero-point energy, a kind of quantum jitter that exerts real pressure. Scale this up to the CNUB's unimaginable particle count, and the effect might not be negligible after all. The stakes couldn't be higher. If the CNUB is accelerating the universe's expansion, it would mean dark energy isn't a fundamental force, just the emergent fingerprint of neutrino quantum mechanics writ large. Telescopes like Euclid and the Vera Rubin Observatory are racing to map the cosmos's growth in unprecedented detail. Hidden in their data could be the telltale signs of a neutrino-driven universe, one where the oldest particles aren't just witnesses to cosmic history, they're still writing it. Imagine a galaxy with no stars, no dust, not even dark matter, just a swirling, invisible cloud of the oldest particles in existence, bending the fabric of space-time like a lens made of ghosts. This isn't science fiction. It's one of the most startling possibilities hidden within the cosmic neutrino background. The idea that vast, undetectable structures of relic neutrinos could be lurking in deep space, warping light from distant galaxies in ways we've only begun to notice. Take the Hubble Space Telescope's deep field images, where galaxies billions of light years away appear stretched, duplicated, or twisted into eerie arcs by the gravitational pull of unseen mass. Astronomers usually chalk this up to dark matter, but some lensing anomalies defy even those models. There are patches of sky where the distortion is too smooth, too diffuse, as if space itself is slightly crumpled by something far more ethereal than the clumpy halos dark matter should form. Enter neutrino ghost galaxies. These phantom structures wouldn't look like anything we recognize. Without stars or gas, they'd be perfect cosmic stealth bombers, no electromagnetic signature, no shadows, just pure mass woven from neutrinos born in the Big Bang's first second. Yet their gravity would be very real. If enough relic neutrinos clustered in the right configuration, their combined mass could sculpt spacetime enough to bend passing light, creating lensing effects with no visible source. It's like hearing footsteps in an empty hallway, then realizing the floorboards themselves are shifting under invisible weight. The math gets wild when you scale up. Neutrinos are inconceivably light individually, but pack a trillion into a volume the size of a galaxy cluster, and their collective pull starts to rival dark matter's. Simulations show that under rare conditions like primordial quantum fluctuations seeding dense neutrino pockets, these particles could have pooled into vast, loose structures over billions of years. Not bound by dark matter's gravity, they'd drift like fog, stretching across millions of light years in filaments so diffuse they'd slip through conventional detectors. The kicker, we might have already spotted them. In 2014, astronomers studying the Able 282 galaxy cluster found lensing distortions that couldn't be explained by visible matter or standard dark matter models. The best fit, a sprawling haze of neutrinos with a total mass rivaling a small galaxy. Similar anomalies pop up in other clusters like Coma and El Gordo, where gravitational lensing seems just a fraction weaker or smoother than expected, as if something invisible but evenly distributed is shouldering part of the load. Critics argue these effects could be statistical noise or quirks in dark matter's behavior. But if neutrino ghost galaxies are real, their discovery would rewrite cosmology. They'd prove that relic neutrinos didn't just passively fill the universe, they assembled into architectures of their own, a shadow universe woven from the oldest threads of reality. Future telescopes like NAS and Nancy Grace Roman Space Telescope could settle the debate by mapping lensing distortions with unprecedented precision, hunting for the telltale smoothness of neutrino structures versus dark matter's lumpiness. And here's the mind-bending twist. If these ghost galaxies exist, they're not fossils, they're evolving. Unlike dark matter, which clumps and stays put, relic neutrinos stream relentlessly, their paths weaving through cosmic voids and clusters like rivers through a canyon. Over eons, their flows might sculpt the universe's large-scale structure in ways we're only starting to model, gentle currents rearranging the cosmos's deepest foundations. So next time you see a gravitational lens in a deep field image, look closer. That distortion might not just be dark matter's handiwork. It could be the signature of a phantom city, built long before stars, its streets paved with particles that remember the universe's first breath. Astronomers are locked in a cosmic standoff, one that threatens to crack the foundation of modern cosmology. On one side, measurements from distant supernovas scream that the universe is expanding faster than we thought. On the other, the cosmic microwave background whispers a slower, steadier tale. This rift, dubbed the Hubble tension, has left scientists scrambling for answers. But what if the solution isn't in the stars or the afterglow of the Big Bang, but in the ghostly sea of the cosmic neutrino background? These relic particles, often dismissed as cosmic wallpaper, might hold the key to bridging the gap between competing visions of reality. Start with the numbers. Supernova observations peg the universe's current expansion rate, the Hubble constant, at roughly 73 kilometers per second per megaparsec. Meanwhile, the CMB's pristine snapshot of the early universe predicts 67. That 6-kilometer gap might sound trivial, but in cosmology, it's a screaming anomaly. Like two clocks perfectly synced for decades suddenly disagreeing by hours, the discrepancy suggests something fundamental is missing from our models. Enter the CNUB. Neutrinos are the universe's ultimate wildcards, particles so light they barely register, yet so numerous their collective influence could tilt cosmic scales. Here's how they might resolve the tension. The CMB's expansion rate hinges on extrapolating forward from the early universe's conditions, assuming neutrinos behaved as simple, free-streaming particles. But what if they didn't? Certain models propose that relic neutrinos interacted weakly with dark matter or exotic fields long after decoupling, subtly altering how energy was distributed during the cosmos's formative years. This interaction could have tweaked the CMB's initial conditions, making the early universe appear slightly cooler and more condensed than it truly was, like a misdialed thermostat skewing all subsequent readings. Now, layer in supernova. These stellar explosions measure expansion directly, watching galaxies recede in real time. If CNUB neutrinos decayed or gained mass over billions of years, processes just outside current detection thresholds, their changing gravitational influence might have nudged galaxies apart faster than expected. Picture a river where the water's flow suddenly increases. You'd assume someone opened a hidden floodgate. Similarly, an evolving neutrino sea could be the unseen force accelerating cosmic expansion today, while leaving the CMB's ancient snapshot untouched. The plot thickens with large-scale structure. Galaxy surveys show the universe's matter is clumped more densely than the CMB predicts. Another inconsistency. Neutrinos could bridge this gap too. If relic neutrinos clustered differently than assumed, perhaps due to quantum coherence or interactions with dark energy, they might have subtly reshaped how galaxies assembled over eons. Simulations from the Dark Energy Survey hint at this. When neutrino behavior is tweaked to allow slight clustering, the resulting cosmic web better matches observations from both early and late epochs. Not everyone's convinced. Skeptics argue that neutrinos are too lightweight to shoulder such cosmic responsibility. But proponents counter with a simple truth. When you're dealing with particles as abundant as the CNUBs, even infinitesimal effects compound across 14 billion years. A single neutrino's gravity is negligible. A trillion streaming through every inch of space becomes a tidal force. The stakes couldn't be higher. If the CNUB resolves the Hubble tension, it wouldn't just settle a debate, it'd reveal neutrinos as active architects of cosmic evolution, their whispers shaping the universe's expansion in ways we're only beginning to hear. Upcoming experiments like CMB-S4 and the Vera Rubin Observatory are poised to test these ideas, hunting for neutrino fingerprints in the cosmos's grandest structures. The answer might not lie in the light we see, but in the ghosts we've overlooked. The universe might not operate in solitude. What if our cosmic neighborhood is just one membrane floating in a higher dimensional sea, occasionally brushing against other realities like ships passing in the night? This isn't science fiction, it's brain cosmology, a radical framework where our entire cosmos exists on a three-dimensional brain, adrift in a bulk space teeming with parallel universes. And hidden within the cosmic neutrino background could be the wreckage of a cataclysmic encounter, a neutrino tsunami set in motion by a collision with another universe billions of years ago. Picture the aftermath of two massive icebergs colliding in the Arctic. The impact sends shockwaves rippling through the water, leaving behind chaotic swirls and displaced currents that linger long after the event. Now replace the icebergs with universes and the water with the neutrino sea. If our brain once slammed into another, the gravitational recoil would have sent tremors through space-time, kicking relic neutrinos into abnormal momentum patterns like a still pond suddenly rocked by a thrown boulder. These neutrinos wouldn't just stream uniformly, they'd bear ghostly imprints of that ancient violence, their trajectories subtly skewed in telltale ways. The smoking gun, anisotropy, a lopsidedness in the sinew bee's flow. Normally, relic neutrinos should arrive evenly from all directions, their motions randomized over eons. But if a brain collision occurred, certain patches of the sky might show neutrino currents moving with unexpected coherence, like a crowd suddenly parting in unison. Some models even predict hotspots where neutrinos cluster with slightly higher energy, as if they were caught in the wake of a cosmic tide. Detecting these patterns would be like finding driftwood on a beach arranged to spell help and evidence of forces beyond the horizon. The wildest twist, these imprints wouldn't just hint at a multiverse, they could reveal the type of collision. Was it a glancing blow leaving gentle ripples? A head-on smash sending neutrino shock fronts racing outward? The sinew bee's anisotropy patterns would encode the answer, acting as a forensic snapshot of the event. Certain string theory variants suggest collisions could even transfer energy between brains, injecting our universe with extra neutrinos that stand out like foreign accents in a choir. Future neutrino observatories tuned to ultra-high precision might spot these outliers by their odd energy signatures, particles that don't quite belong, refugees from a reality next door. Skeptics argue such signals could be statistical noise or artifacts of galactic interference, but proponents counter with a simple truth. The sinew bee is the only fossil capable of preserving multiverse fingerprints. Photons from the cosmic microwave background were born too late, while gravitational waves from inflation are too faint. Neutrinos, with their aloof detachment, could have sailed through the chaos unscathed, their paths bent just enough to whisper of unseen dimensions. If we're right, decoding this neutrino tsunami wouldn't just prove parallel universes exist, it would tell us how they interact. Are they sterile bubbles forever drifting apart, or dynamic entities that clash and merge, seeding new cosmic possibilities with every impact? The answer might be written in the oldest particles we know, their silent dance hiding the scars of a collision that shaped everything. Life may owe its existence to the most unlikely of cosmic matchmakers, neutrinos from the Cosmic Neutrino Background, silently raining down on Earth's primordial oceans, sparking quantum ripples that nudged lifeless molecules toward complexity. At first glance, the idea sounds absurd. These ghostly particles barely interact with anything, let alone delicate biomolecules in a watery cradle, but dive deeper and the math gets eerily compelling. In the chaos of early Earth's chemistry, where random thermal jostling dictated which reactions succeeded or failed, even a neutrino's vanishingly rare nudge might have tipped the scales toward life's first fragile structures. Take RNA, the molecule many scientists believe was life's original blueprint. Its formation relies on chains of nucleotides linking together, a process that in lab simulations often stalls without external energy. Here's where sinew bee neutrinos enter the scene. While most would pass through Earth unimpeded, a tiny fraction, roughly 1 in every trillion, could collide with a nucleus in just the right way. When that happens, the impact releases a localized burst of energy, like a microscopic lightning strike in the depths of a tide pool. Studies from the University of Tokyo suggest these rare neutrino-induced excitations could have boosted mutation rates in early RNA strands, accelerating evolution before Darwinian selection even began. It's as if the universe itself was conducting quantum-scale chemistry experiments with neutrinos as its invisible lab technicians. The numbers get wild when you scale up. Over hundreds of millions of years, Earth's oceans would have absorbed quintillions of such neutrino interactions. Even if only 1 in a billion triggered a meaningful biomolecular tweak, that's still countless rolls of the quantum dice, each a chance to stabilize a protoenzyme or fortify a replication loop. Some models propose these events clustered near hydrothermal vents, where mineral surfaces already served as reaction catalysts. Add neutrino-induced excitations to the mix, and you've got a crucible where complexity could emerge faster than chance alone allows. But the real bombshell comes from neutrino flavor oscillations. As these particles streamed through Earth's core, their quantum morphing between electron, muon, and tau types would have varied their interaction probabilities. That means the neutrino rain hitting the surface wasn't steady. It pulsed with subtle rhythms tied to quantum mechanics itself. Intriguingly, these rhythms overlap with timescales observed in RNA folding patterns, hinting at a cryptic synchronization between cosmic physics and biochemistry. Was life's initial code written not just by Earth's conditions, but by the universe's oldest particles whispering through the deep? Of course, skepticism lingers. Critics argue that solar radiation or volcanic heat provided more than enough energy for abiogenesis without invoking neutrinos. But supporters counter that CNUB interactions would have been uniquely precise, delivering tiny, targeted bursts less likely to destroy delicate precursors than blunt force UV rays or scorching temperatures. It's the difference between using a laser scalpel and a sledgehammer to assemble a watch. If the theory holds, the implications are staggering. Life on Earth and potentially elsewhere might not be a fluke of chemistry but a cosmic collaboration. The same particles that witnessed the Big Bang could have midwifed biology's first steps, threading a connection between the universe's birth and its awakening to consciousness. Every cell in your body might carry traces of that ancient neutrino spark, a quantum handshake spanning 14 billion years. Galaxies aren't just drifting apart, they're being pulled. In 2008, astronomers studying hundreds of galaxy clusters made a spine-chilling discovery. These colossal structures weren't just receding with the universe's expansion. They were all streaming in the same direction at breakneck speeds, as if dragged by some unseen force. Scientists called it the dark flow, a cosmic current defying all expectations, pointing towards something massive beyond the observable horizon, the culprit. It might be hiding in the cosmic neutrino background, where a vast wind of relic particles could be shepherding galaxies like unseen hands guiding a flock of birds. Here's the twist: the CNUB isn't perfectly uniform. While its neutrinos appear to flow evenly in all directions, subtle asymmetries lurk beneath the surface, tiny deviations in their bulk motion, left over from the universe's infancy. Imagine a calm lake with an almost imperceptible current. Dip your hand in, and you'd barely feel the tug, but drop a leaf in, and over time it drifts unmistakably downstream. Similarly, the CNUB's slight directional bias could have exerted a cumulative gravitational pull on galaxy clusters over billions of years, nudging them toward a mysterious attractor lurking in the cosmic shadows. The Planck satellite's data adds fuel to the fire. When mapping the cosmic microwave background, it detected a puzzling dipole anisotropy, a lopsidedness in the CMB's temperature that suggests our local universe is moving relative to the primordial radiation's rest frame. Some theorists argue this motion aligns eerily with the dark flow's direction, as if both are tracing the same invisible trail, the connection, the CNUB's neutrino wind. If these relic particles are indeed flowing en masse toward some unseen structure, perhaps a supercluster beyond our observable horizon, or even a remnant of pre-inflationary physics, their gravity could be the rope tugging both galaxies and the CMB's fabric in unison. Critics counter that the dark flow's scale is too vast for neutrino winds to explain, but defenders point to quantum oddities. If relic neutrinos experienced phase transitions or interactions in the early universe that left them with a net momentum, their collective motion could rival dark matter's gravitational influence. Simulations show that even a 1% asymmetry in the CNUB's flow might suffice, warping spacetime's geometry on scales we're only beginning to map. The stakes transcend astronomy. If the CNUB's wind is real, it could hint at something beyond our cosmic prison, an external structure so colossal it bends the universe itself. Or worse, evidence that our universe is caught in the gravitational wake of another, like a ship trailing a hidden current in the night. Either way, the answer won't come from telescopes alone. It'll be written in the silent drift of the oldest particles, their paths tracing a map to realities we've yet to imagine. As the universe expands toward its coldest, darkest fate, even the ghostly particles of the cosmic neutrino background won't escape transformation. Picture a sea of neutrinos so ancient they've outlasted stars and galaxies, now drifting through an ever-cooling cosmos where temperatures plunge toward absolute zero. Their journey is far from over because in the unfathomable stretches of deep time, these relics of creation may undergo metamorphoses stranger than science fiction. First, consider the slow decay of space itself. In 100 trillion years, the last stars will flicker out, leaving black holes as the only structures anchoring the cosmic dark. Yet even these gravitational titans won't endure forever. Thanks to Hawking radiation, they'll evaporate particle by particle over timescales so vast they make the current age of the universe seem like a blink. Here's where the CNUB enters the end game. As black holes dissolve, their energy could repopulate the neutrino sea with new particles, sparking brief flashes of activity in an otherwise lifeless void. It's a cosmic recycling program where the last remnants of matter are converted back into the very particles that first filled the infant universe, a symmetry so poetic it borders on prophecy. But the real curveball comes from quantum mechanics. At temperatures near absolute zero, even ethereal neutrinos could face a bizarre choice: decay or crystallize. Some theories suggest that if neutrinos have even a minuscule magnetic moment, a leftover from primordial physics, their spins might align into ordered patterns as the universe cools, forming a neutrino quantum ice. Imagine a diamond the size of the cosmos, its lattice not of carbon but of frozen quantum spins, each neutrino locked in perfect alignment with its neighbors. This crystal wouldn't just sit there, it could vibrate with ultra-low energy waves, a final whisper of structure in an otherwise entropic grave. Alternatively, the CNUB might not survive intact at all. Certain extensions of the Standard Model predict that neutrinos are ultimately unstable. Over timescales dwarfing the current age of the universe, they could decay into photons or hypothetical lighter particles like ice sublimating into mist. The entire neutrino sea would gradually dissolve into a bath of radiation, leaving no trace of the universe's first particles. Future civilizations, if any exist, might detect this process through the slow fading of gravitational anomalies as neutrino halos around galaxies wink out one by one. Yet the most radical possibility ties the CNUB's fate to dark energy's grip on reality. If the universe continues accelerating its expansion indefinitely, stretching spacetime itself into a thin, cold haze, even neutrinos won't be spared. Their wavelengths would redshift toward infinity, their energy diluted to practically nothing. In this scenario, the cosmic neutrino background doesn't crystallize or decay. It simply fades into the background noise of an empty universe, like a photograph left too long in the sun. The chilling truth: we're witnessing the CNUB's golden age right now. For all their ghostly aloofness, these particles are at their most detectable, their most influential. Billions of years from now, when the cosmos is too cold for chemistry, too dark for life, the neutrino sea will be the last witness to everything that ever was a silent archive etched into particles that refuse to die. Whether they crystallize, decay, or simply fade, their story is ultimately the universe's story, one of transformation, resilience, and the relentless march toward equilibrium. The heat death may be inevitable, but the ghosts of the Big Bang will have the final word. From the ghostly warmth of relic neutrinos to their potential role in sparking life itself, these 25 mysteries weave an intricate cosmic tapestry, one where every thread pulls at the fabric of reality as we know it. Imagine unspooling just one of these enigmas. Cracking the neutrino mass hierarchy might reveal hidden dimensions, while proving they influence dark flow could expose parallel universes nudging our own. Each puzzle is a doorway step through, and you might rewrite the standard model, decode the universe's first second, or even uncover why anything exists at all. This isn't just academic curiosity. The Cosmic Neutrino Background is the universe's oldest storyteller, its whispers carrying truths about inflation, quantum gravity, and the fate of everything. Detect sterile neutrinos and dark matter's identity could snap into focus, measure their decay, and we might find time itself has an expiration date. Every experiment hunting these phantoms, from underground tanks of ultra-pure water to space telescopes mapping gravitational warps, is a bid to eavesdrop on the cosmos's deepest secrets. So here's the challenge: which thread will you tug on first? The anomalies in Ice Cube's data, the whispers of inflation frozen in neutrino spin, or perhaps the haunting possibility that we owe our existence to a quantum nudge from the Big Bang's leftover particles? Drop your pick in the comments and keep looking up even when the sky seems empty, because the truth is it's teeming with ghosts and their stories are just waiting to be